So I'm here today. My name is Sergio, and I work at Thousand Eyes. And I'm going to present how we architect a global system that monitors the internet performance in a global scale. So we try to give visibility into the networks that our customers and users don't control. And this is something that's very hard to achieve. Everyone struggles with it. We're moving more and more to cloud services, and we depend on the internet for delivery of our software. And having visibility into the internet and how it's being delivered is the thing that's becoming more and more important. So I'm going to start with presenting what Thousand Eyes does, so we have context on what we do. I'm going to give you an architecture overview of how the system was actually built and some insights and pitfalls about our architecture. And then I'm going to talk a bit about the cloud state, which is a study that we do every year. We started last year about how cloud connectivity on the internet can affect your deployments. So we look at AWS, Azure, GCP, and this year also Alibaba. And you can use this report to actually understand how the delivery of your services can be affected depending on the cloud provider you use. So before we start, we can just present Twitch to the person next to you. This was a request from the conference, and tell what you do and what you wait for this presentation. I'm going to give you 1 minute for that. There's not much people, so it's going to be fast. So what does the world needs us? So basically, as I said before, everyone is using the internet to deliver their services. To also, like when we work day to day, we need the internet. But basically, we're sharing the same internet, which is a beautiful thing, by the way. We share the internet also with the kids, with everyone that's seeing cats videos. And that means that we might be affected by that traffic. And we need to have visibility if our actual application is being delivered correctly. Next slide. Yeah. So what do we do? So we want to give you the visibility of looking at the internet, looking at the networks like they're your own. And we also, with all the data we collect from the internet, we are able to show you, even if you don't have any tests running to specific locations on the internet, you can receive alerts that there's an outage going on the internet that may affect your service delivery. I'm going to show now an example, so it's more attainable. There was this DDoS attack, denial of service attack in Wikipedia in September the 5th, if I'm not wrong. And we are monitoring Wikipedia in this case, and we're able to see the rollout of the events, what's going on. And this, you can see here that there was a drop in availability. It started more in Europe because the services were being affected, that were the ones that were serving the traffic in Europe. And then you can see here, after a couple of minutes, this is the timeline, and you can see here the availability being affected. And you can see here that servers, that this is agents, started being affected also in America. And afterwards, yeah, here you can see that average response time of the service, which is usually very low, started to peak because of the denial of service going on. And all the traffic, additional traffic that the Wikipedia servers would have to handle. You can see here how much time we're wasting in the different phases of the connection. Moving forward a bit more, we can see here that some services stopped responding completely. So the traffic was not reaching the servers at all. So there was no response at this point. Looking at so one of the things about the way we visualize the data is I can see the layers of the stack. So we started at the application level, and now this is the network level. And you can see here on this side that these nodes here on the internet were not able to reach the destinations. So that's the main problem, because the denial of service was actually creating so much load that the traffic could not be handled. Moving forward, so usually when the denial of service attack happens, what companies do is mitigate the problem, trying to reroute the traffic, and trying to clean it up to remove the requests that are coming from the denial of service. To do this, you can do it on your own, or you can actually request by a service that does this traffic cleaning. And you can see here, this is the BGP layer. So just so you know, if someone doesn't know actually, BGP layer is the control plane. So it actually determines how the traffic will flow to the internet. And you can see here that at this point, the traffic was going to the Wikimedia Foundation autonomous system. But you can see here that Cloudflare started to clean up the traffic at this point. So they started basically changing the BGP routing and introduced their servers on the path. This is still ongoing, so it's still red, so it means that there's a path change. And after this, you can see here that the traffic is completely clean, and it's going through Cloudflare services. And Cloudflare is actually doing the traffic cleaning, so removing all the ones that they identify as denial of service attack, and letting go through the actual requests. And in the end, with this approach, going back, you can see here that after this happened, the latency went down and the availability of the application was fixed. This is actually, so if you want to see this, we have this concept of snapshots, so you can actually just share this with everyone. So we have a blog post in our 1000 Eyes blog, and you can actually interact and see what I explained here. You can actually see the different layers, and you can see here the traffic, the BGP routing, and the changes going on. So if you want to actually, oh, sorry, you're not seeing this. Yeah, why not? It was there. Okay, doesn't matter. But yeah, if you go to the 1000 Eyes blog, you can see there, and you can actually click and visualize the information, which is very interesting. So now, how do we do this? That's the most relevant part on this talk. So we have a bunch of different types of agents that are on the internet, and we try to create synthetic traffic in most cases to mimic users actually using our services. And we have cloud agents, which basically is our own cloud of agents that we manage, and you can just run your tests from there. And then we have enterprise agents that you can install in your premises, and you have endpoint agents that are running in your machine, in the end user machine, like I have one here, which I'm going to show some data. So we have quite a lot of coverage through the world. We also have coverage outside the cloud providers, so that's a big plus because you want to have visibility outside of your cloud providers, so you know what the actual users are feeling. We have ISPs, so we try to get closer to what the user is actually seeing. In terms of what we do, so we try to resolve problems across the stack, so you can have visibility into different layers, as I've shown before with the Wikipedia example. We also use this, so we use our own service to look at our SLAs. So if we are respecting our SLAs, and this is an example where a change on our internet configuration basically change the routing, and half of our customers were not able to reach our control plane, and we were alerted by our own platform, and we are able to fix it in a very short time. So we actually use our own platform to monitor our services, which is also a big plus. So how do we do this, which is the most important part? So in terms of, I was thinking about what's software architecture now, and it's more or less a definition of the living document that's on Wikipedia. So it's a set of fundamental structures that defines how the software system should behave and should look. But this is not a fixed document. Before you had this concept of architect, we still have it, but it would be like someone would just write your architecture and it will stay more or less immutable, more or less. But nowadays it just evolves. The engineering teams that are working actually are day-to-day looking at the architecture and making changes to adapt to the new features they want to develop, or to the increased traffic, which happens a lot. So if you are a startup, you have low traffic, but then when you grow, you start having more traffic, and then your software architecture changes because you want to cater for more traffic. You don't want to start with a really complex architecture with a low number of users. It will be expensive in terms of running the actual architecture, but also it will be expensive to make it happen. So this is really high-level architecture. I just want to give this slide because this was a decision in terms of architecture that was made 8 years ago, probably, when 1000i started. And this shows how, in terms of how we manage our agents, how we collect our data. Basically, we have a control plane and a data plane. Since we are a networking company, this pattern comes from networking. We have the control plane that defines the routes, and then we have the data plane where actually the data flows. For us, the control plane just controls how the agents, what the agents will do, which tasks they will execute, and the data plane will basically receive the data points that are collected by the agents. So this is a very important pattern for us, and this is the one that still holds. And this is just an example of how a software architecture can hold even nowadays for many years. In terms of the control plane, so going a bit deeper, this is very simplified, but just to have an idea of what's going on. So we have here the agents that are running on external networks, and they have a control layer, which will have a controller. We actually use Kubernetes, so it's just Docker containers running. Then we use Kafka as message queue, a message streaming platform. And then we have a bunch of shared services, which is microservices, and they just, in this case, they will just return which tasks, which actual tests the user wants to run, and where does it want to run. And we'll also say, so each agent will know to which data plane to actually send the data. So the control plane will have full control of the agent and what it's doing. This is a very important pattern for us. Another important layer is the schedule layer. This is used because, for example, on the agents that are on the end user machines, they're very dynamic, so they are moving around, and we need to schedule actual tasks to run on those. So we have this concept of like label. So we label the agent according to their location, to the network where they are. For example, my agent now is in Berlin. I can create a test that's on Berlin location, and the scheduler, when I check in, it will know that I'm in Berlin and will actually assign the test to Berlin. And then all the information, time series data, which is not used in this case, the storage metadata will be stored in MySQL and MongoDB. That's the two data stores we are using in this case. But this is the overall architecture. It's used by all agents. And then we have the data plane, which is looks like a data processing pipeline. And the main thing we have here is actually the data pipeline. So we receive the data. We don't write the data at the moment we receive it. We don't write the data immediately to our storage layer, because it means that if our storage layer is down, we cannot receive the data. And that's a problem that we had before when we started. And then we introduced it, we're actually using Kafka. So when we get the data points, we write them to Kafka, and actually they will be stored there because Kafka has properties of storing. We won't lose the data points. And then we have this data pipeline that will enrich the data. So we have a bunch of, like, for example, we determine which location of the IPs, so it's more rich, visualizing the information. And then we write it to Mongo in the time series data. And we also have indexing and Elasticsearch because we do online aggregations to show on the views. And then we have alert processors, very simplified, this one, that will actually process the data. We'll have the alert rules, and we'll alert if needed. We also have a bunch of shared services that are shared among the control plane and data plane, and also the front-end application and the actually API. In terms of the work that we've been doing in the last couple of years, so I've been working at 1000i for 2 years. When I started, we have this big monolith still, which is a common pattern in companies that grow from a startup. So when you are really small, a monolith makes sense. It's a small team, a small code base, easy to manage. You can actually achieve results faster. You don't have to deal with all the complexity of managing services. Of course, nowadays with cloud providers and all of that, it's way easier than before. So the path we've been going through is actually breaking down that monolith into microservices, but also into micro frontends. So that's what we are in this moment. We already did the part of the microservices on the back end, and now we're working on the micro frontends. And what's the difference here is that we can serve parts of the application from different front ends. I can try to give you a demo here. If I can make this go to the, yeah. So here on this page, which is just an overview page, doesn't have much data, but it doesn't really matter. You can see here that this container in the inside is actually being served by a micro front end. So the external part is a different service. And if I go here to the network layer, let me just refresh the page. Yeah. Where is it? Just change my account. Yeah, at this point, this is actually being served. I need to change my. Let me just 1 moment. This is actually being served. We use feature flags, which is actually a thing that you should use. Probably everyone uses it. And this is under the feature flag. I will just log in with the feature flag active, and you'll be able to see that that page that was coming from the normal server, the server that served the rest of the application, will actually be served from a micro front end, of course. This is the good things about single sign-on. Signing in. All good. I'm just going to go to this overview page. And this is a feature flag. I'm going to enable unstable features. You can see here. Can I find the, yeah, what I can show you here. So basically, you can see here that this is the logs from the server, and it's actually requesting the overview bundle that was bundled, and this is the snapshot version that's being served. So it's actually calling the micro front end and serving this part of the application to the micro front end. So it means you can package it in a different way. And actually, the main thing we get from this is we can release that, for example, that page, we can release independently from the rest of the application. And this is a really interesting thing because many companies, they go and have microservices, but then the front end is still a big application. And with micro front end architecture, we can actually break down the front end and be able to deliver the front end by domain, which is the main thing that we want to achieve, is split our architecture by domain and by team. So each team will be actually responsible to deliver the full stack. We can do it later. Maybe it's better. Yeah. Yeah, in terms of why microservice architecture, there have been many talks about microservices, so I don't go very deep on this. There's pros and cons. In our case, it worked very well because there's issues there, but having the monolith was already an issue in terms of the build size and being able to run all the tests that we wanted to run before deploying the service, and having independent releases is also a problem that we had before. So in terms of microservices, what we try to do is create services that have their own domain, and this allows teams to have ownership on their services so they can release whenever they want. When they have changes that make sense, they can just release them without having dependency on other teams. This is the main gain we got from the microservice architecture. So it also enforces boundaries. Like if you have a monolith, of course you can use libraries, and that's also a valid pattern. And you should also use it even when you use microservices because you want to have shared code among microservices. And you can use libraries for that. But when you have a monolith, there might be a tendency of just writing code there because it's easier. But then you get all this entanglement. You need to be more strict. With microservices, this boundary is set. You can also do it wrong, but the boundary is easier to define and easier to see by each team. So yeah, this is just a summary of what I said. It also allows us to scale each microservice in a different way. When you have a monolith, you're going to scale all the dependencies around it, so all the actually APIs. And with microservices, you can scale them independently, which is also a big plus. That's also a big plus from the control plane and data plane approach, because control plane also has different needs from the data plane. Data plane is processing data points. It needs to be fast, it needs to be high speed. So it has much more scaling issues and scalability problems that we want to solve. The control plane it doesn't need that kind of scale. So also the difference between the control plane and data plane is also there. Of course, there's challenges. There's how to communicate between the services. We're using two approaches there. We're using REST and gRPC, depending on the service. It really depends on legacy too, because before we are mainly using REST. New services, we use gRPC. It really depends on each team and what they want to decide to do. Also, of course, like simple activities may take longer because you have to call multiple services, but that's not a big deal usually. And when you go to microservices, you also move towards a more event-driven flow, which is also what we saw in the data plane when we do message processing. This is also a change on how you actually do software development. And then there's the important things about how to actually deploy them, like circuit breakers. You don't want to just overload your services when they are not responding. So you need to implement such circuit breakers to break calls when the service is not responding, so you don't overflow your full infrastructure. And the other issue we have is distributed tracing. So now, when the monolith is very easy, you have the logs. You can look at the logs, you have monitoring and all of that. It's all in the same place. It's all there. In microservices, there's a need for distributed tracing. You need to know the service that's coming in on the load balancer. It's going through a bunch of microservices until it reaches the database layer or any other layer. You need to know where is it failing. So distributed tracing is a thing that you need. And it's something that we didn't have in the beginning, but the more you have microservices, this need will actually, you will have to solve this need at some point. Yeah, then like in terms of deployment, you have to automate everything because all the teams will be deploying at different points in time. Your testing needs to be really on point. Yeah, when you actually, on your pipeline, when you promote your service to staging and then to production or whatever environments you have, you need to make sure that it won't break. You need to have ability to shift traffic, if possible, to the new service and look at the error rates, latency, all those metrics that are important for your service. You need to know before you shift the whole traffic to a new version if the service is actually responding as you defined. The other thing is that the worst thing that can happen in microservice architecture is copying code around. So having duplicated code, which will make your life even worse. So we need to explore ways of doing it by doing domain specific things and also using libraries, of course, to have shared code. In terms of infrastructure at Thousand Eyes, so as I said before, we use Kubernetes, which is something that's already been talked in this conference. So it's basically container orchestration. The good thing about Kubernetes is that the engineering teams are fully responsible for their services, so they actually manage the deployments, and they don't have to involve anyone like directly from infrastructure. We also have Kafka, Redis, MongoDB, MySQL, and Elasticsearch clusters that we run ourselves. We have our own data center, so we have our own bare metal servers. We also use cloud providers different ways. We use cloud providers for the application itself. We also use another cloud provider for all the monitoring and alerting stack, and to have separation of concerns in that case. So we are using kind of a hybrid architecture, which is the monitoring part is really important for us, having it in a separate provider. In terms of the software stack, yeah, I already said that Kafka, distributed streaming platform, Redis for caching and PubSub, MongoDB, long-term storage. Everyone asks why MongoDB. Well, it was a decision that was made. It's not easy to justify why, actually, but it was made this way. There are other technologies, but this is what we have. And it actually has been working for us. There was some effort in the beginning to actually make it work as we wanted, but now it works. Probably it will change in the future, I don't know. There's MySQL for metadata storage, and we also introduced Elasticsearch, actually in the last couple of years, last year and a half, because we wanted to have real-time aggregations, and MongoDB had some performance issues with non-indexed properties, so we just used Elasticsearch for these cases. And actually, using microservices and this new approach make it easier to introduce Elasticsearch into the stack. I also think now it's easier to actually replace MongoDB or any other of the other data storage with this new architecture, and that's a big plus on this side. In terms of scaling strategies, when you are managing a bunch of agents that are not in your network, they are in external networks, there are a bunch of things that you need to be aware of. When the backend is not available, there's a big thing about it. So you should buffer the information, so you don't have to overload the backend. If it's not available, you can wait. You can just buffer the information if needed. And actually, when the services come back, you should be careful not to overwhelm the backend with sending all the data we have. So we have some mechanisms to actually spread the data when the backend comes back to life. We just spread the load through time, so we don't overload the backend. There's also the partitioning data, so try to partition data as much as you can. This will allow you to scale, and also, if you have good partitioning keys, you'll be able to create more instances of your services and actually spread the load. This also applies for the agents, of course. We have concepts of clustering, and agents can cluster and run their tasks and spread the load of running their tasks in the external networks. So this doesn't apply only to the backend. It also applies to if you're managing software that runs outside of your network. Is also an important thing to do. Always batch your reads and writes. This is very important because of course, performance when it's possible. And for metadata, have distributed caches. We are using Kafka streams a lot for this. So you don't have to query MySQL all the time. MySQL is just seen as a storage mechanism, but then you use caches to achieve the performance that we want. And in terms of issues I have in running services in Kubernetes, it's the usual things. Adequate readiness and liveness. You don't want your service, when it's not ready to serve your request, you don't want it to actually be put on the pool and start responding to requests. That will be bad for you because there will be 500 and your service will be down. Also, liveness probes is also important. One important thing here is when the backing services are down, like if you depend on MySQL, it doesn't make sense to just keep restarting your service because it won't make any difference. So one of the things that we noticed is in the beginning, we had some issues there because the services would restart if MySQL was down, for example, and this didn't have it actually just increased the load on the system. So be careful with how you define your liveness probes and readiness probes. And then there's be able to observe what's happening. That's more on the observability side. You need to be able to know what your application is doing and be able to observe the results and alert on those if necessary. It's also very important for debugging. Also having the ability to change the percentage of traces you are actually collecting from your system is also very important. So usually you won't collect, you will collect like 10%, 5%, 1%, depends on your scale. But at some point, you might want to a specific service to collect more traces so we have more visibility into what's happening. So having this control is also very important for us. Some Kafka pitfalls. We have an article on the Thousand Eyes engineering blog if you want to take a look. Yeah, one of them is like the usual things of partitioning, like choose well your partitioning keys. You don't want to have your topic have a specific partition with all the load, and then one of the services, one of the instances that are managing this partition is just overwhelmed, and the other ones are doing nothing. So your partition keys are very important. The number of partitions for each topic is unlimited, theoretically, but and helps you parallelize your data processing, but there's overhead on that. So it really depends on your size of the cluster, but you really have to understand what's your size of your cluster to understand how many partitions you can handle. The other thing is network I/O. So some applications, if you have like really large documents, if you are using JSON, for example, you can, one service or a bunch of services consuming data from Kafka can really overwhelm your network, and this can become an issue. So be aware of how much network I/O you're actually using when you're using Kafka. And also had issues with the topic deletion. That's on the article, on the blog post. Some settings that we had in Kafka related to segmentation were not allowing Kafka to actually delete the topics, and they were just growing over time. There are more details on the blog post. MongoDB, the same thing, partition keys, chunk migrations, like look at your chunk migrations, if they are happening or not, very important, because moving chunks around is one of the ways MongoDB has to handle the load across the shards. Yeah, be careful in creating indexes, because they create overhead on the system. And then, yeah, when you run queries, just make sure they are right. Yeah, we have seen queries that can take down a cluster. Not take down, but they will slowly slow down the cluster until it will become unbearable, and you have to find where they are running. And this also applies to running actually queries on prod, which should not happen. But if someone runs a query in prod, it should validate if that query is correct. And last but not least, this applies to any sharding. Never do skip and limit for pagination, because basically there's no way, if you have multiple shards with data, when you do a skip limit, basically you will have to retrieve all the documents from all the shards until that limit, and then the client, or in this case MongoOS, will have to just look at all the lists, put them all together, and then apply the skip and limit. But that means that all the documents will come from the shards to your client, or to MongoOS in this case, and it will create lots of traffic, and it will be very inefficient. So that's why also Elasticsearch doesn't allow this kind of pattern. One important thing about gRPC that we use, gRPC load balancing, something that there's an article on the Kubernetes website. It's called gRPC load balancing without tears. So it makes people cry. Maybe it made us cry one day. And it's very important because gRPC uses HTTP2, if you don't have any load balancing, you will basically be bounded to one instance only. There will be no spreading of load like happens in HTTP. So make sure that you put in front of one of the techniques, there are others, is putting in front a load balancer that actually will manage the HTTP2 connection into the different gRPC services. In terms of the actual delivery, how do you do it? So we've been changing this over time. Kubernetes helps a lot in this case. Currently, we are maturing. We're not top level, of course, but we are maturing our process. When I interview people from Google or that worked on Google or Amazon, when they explain how they deploy the services, it looks very simple, and most of them, or some of them, don't have the notion of how much valuable it is they deploy in pipeline. You just have to put it there, and it will eventually reach production, and it's just magic. Some of them don't see really the value of their pipeline, and it's really something hard to achieve if you have to build it yourself. And there are not many tools that actually do it really well. There are a bunch of them. Now, at this moment, we are implementing the GitOps approach. So basically, all our infrastructure, all the deployments are defined on Git. We have our deployments, our services, and we use the Git model. Basically, we use PRs, and everyone reviews the PRs. What's the advantage of this? It gives you visibility because everyone can see the changes on the infrastructure and when the services are deployed. It's also auditable, so it's very important for auditable purposes. You can know when the service is deployed and why and when and by who. And also that gives you security because only authorized people can actually merge those changes. And, oh, let me go back. And actually, this is also an example that I took. This is basically just a PR request, and it will just define a service. And we are using Customize from Kubernetes in this case. And we'll define the service deployment and the ingress. And when it gets merged, it will get deployed to the different environments. We can also define different environments. It will get deployed, and it's auditable. So anyone can look at this PR, and actually it makes it way easier to manage deployments. My thing is crazy. Another important thing is when you're dealing with external clients, in our case agents, you need to roll out gradually. It's very important if you are in your premises, but it's under your control. But if you have a bunch of agents running in many places in the world, you have to roll out gradually. That's what we do. And this makes us understand if there are issues with our deployment. Because we have agents running in the end user machines, and having to ask the users to do anything, it's almost impossible or very hard. So we use automated rolling outs of the new features, and we have monitoring to see if there's any errors, if there are any problems, and then we can roll back to previous versions. We also have auto updates. It's pretty similar what you have in Chrome, for example. Pretty similar. It works very well because if you deploy all of them, and for example, you break your update system, it kind of stuck. You have to contact everyone and basically redeploy everything. Yep, so in terms of architecture, that's what I have today. I just want to give a brief, interesting point about the study that we have. It's called State. It's basically, with all the data we collect from all the users, we build this study where you can actually see the connectivity between the different cloud providers, but also how external users would see your services when you are serving from specific clouds. And this is, because this, from data and from the actual internet, from the actual tests we have, it's real time, and it's actually will give you a pretty accurate view of how the cloud providers are defining their internets, which is something sometimes not visible for someone that's selecting a cloud provider. It's very hard to get that information. So if you want to join, and there will be in 13th of November, we're going to present this study of this year. It's you can download the full article. It's free, and you can actually use it to when you're doing your architectural decisions on about the internet side of the network side of things when selecting your cloud providers. This is the final slide. So if you want to rate my session, please do. If you want T-shirts, nice T-shirts from Thousand Eyes, just drop me an email and I will send it to you. So we have 4 minutes for questions. I don't know, do we have a microphone?
Thank you. Could you describe the way you do in micro frontends? How do you compose the final models, final website, and approaches you're doing? Yeah.
So what we're doing is on the front end we use Vue.js. So we have a container on Vue.js, and that's the main one that I was showing on the web page. And then we package the micro frontend in a JS file that will get loaded into the page when the page is loaded, and it will go in that container, and will basically build all the things around it. The only thing about it is it's not that hard to achieve that, but you have to route your requests to the right micro frontends. So you need to be careful about that. And there's another thing about The routing phase is because you are releasing the micro frontend in a different cycle. You need to be aware that you have to keep the previous versions being served in the front end, in the micro front end, because the customer can be loading old versions, and you still need to serve the old JS files. So what we do is that on the micro front end, we keep the latest versions, all of them, in the micro front end service, so it doesn't fail.
And for example, from release synchronization, you need to release different parts and synchronize them eventually.
Well, they don't need to be synchronized, but you need to make sure that there's no breaking changes in between releases. If there's a major breaking change to the way we do the micro frontends, then we need to synchronize everyone. But if everyone keeps the same model, they can just release their parts, and theoretically there will be no breaking changes, so nothing will break. But in the end, when you release a micro frontend, you should run your end-to-end tests or whatever smoke tests you have to make sure that you didn't break anything on the application. But theoretically, that shouldn't happen, only if you do really weird things.
Thank you.
Yep.
Question: how do you actually develop these micro frontends? How is the development experience? You know, because you are developing one. How is it attached or detached from this kind of main page where it's going to be like rendered?
In terms of like where the actual JS file is served from, or
no, when you're developing this one thing.
Oh, okay, yeah. That is an issue. If you have like multiple micro frontends, when you are developing it, we use Docker Compose to actually be able to have all the micro frontends around. But that is a challenge of having not just the micro frontends, but also the services behind them, so the backends, having them all in sync for your developer experience to be good enough for your development. It's a challenge for us because. For now, our micro frontends is basically each page is a micro frontend. So you see the main container. It's not much of a deal, but when you move forward and you have like several micro frontends around that have communication between themselves, that can become an issue. And you have to explore ways of the actual developer be able to have the full experience, because you cannot just develop your micro frontend and not see the rest. And that is a challenge for development.
Awesome. So thank you, Sergio, for
Thank you.